Our recording.
Okay, so thank you everyone for coming on today's TUCS talk. Presenting today is Jonathan Davidson, who is a PhD student here at UTAS, who does his research in PS3 development apparently. Is that correct?
Pretty close.
Excellent. Okay, so firstly a few announcements. At the end of the talk, see somebody, I think it will be Michael Ford, to register that you're here for your TUCS scheme points to go into the draw for our iPod at the end of semester. Along with that, at the end of semester, we will be running lightning talks again. So rules will be similar to last semester's, and we'll be posting an official announcement next week. Get your ideas happening as soon as possible. We'd love to see more than the number of talks we had last year. So everyone, please welcome Jonathan.
Thank you very much. It's great to have this opportunity to muck around with technology, but now I can do that. Hooray! So it's working. Right. So I am talking today about programming on the programming for the Sony PlayStation 3, which is there's a black box down the front here. It's that one. And talking about some of the aspects of the hardware in particular. So it has a very powerful processor in it, but it's a bit unusual to use. It's not as simple as writing a program that just does what you want it to do. You have to do a bit of extra work to get access to the full power up. So what? With a bit of luck, we'll start here. And there we go. This is a fractal renderer, a Mandelbrot fractal. Now, Mandelbrot fractal, very simple equation that describes it. Z maps to Z squared plus C. So for each of those points, that's the calculation that takes place. C is a complex number that describes the position of the point in terms of X and Y. Z is a number, is the result of, starts at 0 for each one. And once that part of the equation gets above particularly 4, a distance of 2 away from the centre, square of, etc., hypotenuse, triangles, etc. It's deemed as having escaped, and the colours are dictated by the number of iterations that take place before the point escapes. So we have here a very slow scanning fractal renderer at the moment. It's taking approximately, off the top of my head, but approximately 25 seconds for each pass. So we'll continue at this point by looking at some of the code that's used to generate that. And it's done using a fairly simple program that what it does is it loops through for each point and it iterates that equation, that multiplication on each point. And so you'll see here, if I do it that way, in the middle of it in particular, there's a couple of multipliers and a couple of additions. There is a real part and an imaginary part to the position, the X and the Y. So we have some multipliers and some additions in the core of it, and that happens inside this loop here. So this inner loop controls the number of iterations per point. The next loop out is looped once for each X position, and the next line out is it's done once for each line. So it scans across, as you saw, one line at a time. Now this is a program that is running on the PPE. The Cell BE processor has a number of cores within it. You have a PPE and you have some others. We'll start with the PPE. Now the PPE, I'll do this just for legible. There we go, the Cell Broadband Engine. It has 2 threads of execution, and it's running at around about 3.2 gigahertz. Now, it's not actually a particularly exciting processor in any way. 3.2 gigahertz sounds like a reasonably big number, but if we actually time a single run of that program, it will spit out a number telling me how many seconds it took to run. Now, this is running on just the PPE. It's the general purpose part of the Cell BE processor. It's kind of like a G5 processor that you would have found in a Mac from a few years back before they switched to Intel. But 3.2 gigahertz, but they left out most of the interesting bits that make code run fast. And so for unoptimized code, what you find for this, there we go, 30 seconds in fact, 30.6. Does that show up on the screen? It does too. So 25 was a bit optimistic. 30.6. They've left out a lot of interesting bits. So comparably, one of the closest comparisons to the Cell BE PPE in terms of performance is an 800 megahertz Pentium 3. So the PlayStation 3, computing with the power of a Pentium 3 processor from a long time ago. Not particularly exciting. One other thing I want to say is, as I go through here, if you have questions, wave your arm, call them out, do something. I'd much prefer this to be interactive in some way. I don't really want to go through from start to finish being the only one to have made a noise in the room. That isn't why I'm here. I'm actually here to try to convey something about this, and the more it makes sense to you, the better I can do that. So, the next step in improving the performance here is actually to say, well, what else does the Cell BE have as a processor that might be able to help us draw this stuff quicker? And the next thing that is worth noting is that on the Cell BE processor, there are not just PPEs, there are things called SPEs. So PPE stands for Power PC Processor Element. It's kind of long-winded. And SPE stands for Synergistic Processor Element, which just sounds ridiculous. Regardless, SPEs is what they are. And so they are on the processor. So that what we'll try now is we'll try running our program on the SPE and see what performance we get. Now, the first thing to note about an SPE is that it has 256 kilobytes of its own memory. So the way a program is run on the SPE is it's loaded off disk by the PPE, it's sent across the memory bus into the SPE, so it's loaded into the SPE, and then it runs on the SPE. And while it's running there, it's responsible for transferring data in and transferring data out, all by itself. It's almost like an individual little system on a chip. So what we need to do is that there's modifications that are necessary to the program to make that work. So I'll stick the first part of that up on the screen. And of particular note within it, we scroll through, we see that amongst all the other noise in here, there are these lines. So, but there are these lines which describe the process of creating an SPE context. So an SPE context is something for the operating system to manage the program that's running on the SPE. We then load a program, so load an actual program from disk to be used within that SPE. And then the next steps are to actually create a thread to run that program. So the way these the SPE programs are scheduled, there are operating system threads, or P threads in this case, which are used to basically hide the fact that there's only one PPE trying to manage multiple SPE threads as well as doing its own thing. So basically we take the context, stick a program, attach a program to the context, whack it inside a thread, and then say thread go. So the P thread create, go thread, run the program. And passed with it, there's the address of the thread structure here contains information for that PPE, for that SPE program. So the SPE program runs, it gets told some things that it is to draw, and it gets on and draws them. And then when it's done, so this pthread join function call blocks, sits there and waits, twiddles its thumbs until that thread completes, and then the program exits. So that's the first part of this. So if we run this, what happens? Doesn't seem right. There's a lot of blank in that. This is illustrating the fact that an SPE, for a start, SPE has 256 kilobytes of memory. This is currently running at 720p because the projector doesn't look any good at 1080p. But at 720p, so 1280 pixels across by 720 lines down, multiply that by 4 to get the 32-bit value that describes each pixel is a lot more than 256 kilobytes. Someone can work it out and shout it out to me at some point if you like. But it's not all going to fit. But the step beyond that is, even though there's 256 kilobytes of memory, a single DMA transfer, the way an SPE interacts with my memory is there's a DMA engine called the memory flow controller, and it takes data and it copies it to my memory in chunks. And the biggest chunk possible is actually only 16 kilobytes. And so that is 64 by 64 pixels. Isn't it great? So the next step is to actually say, well, we can't do it as just a single transfer. We need to do it as several transfers. And so we move on to the next one. If we have a look at this piece of code. Now this program, which I skipped over for the last version, this program describes what's running on the SPE itself. So if we go through it, get to the end of it, what happens is we have the main function. It's a great place for a C program to start. Begins, and the first thing that happens is we see that there is this MFC get function. So memory flow controller gets me some data. And so it goes off and it gets this structure, this args structure. And that's the arguments, the parameters for which this run of the SPE program are to be useful. So we can actually change the parameters and have the same SPE program that draws different types of fractals, or at least different settings of fractals. We'll look at those a bit more later. So we pass an argument structure to it, but the first thing that happens is it's only given just enough. It's just given the pointer to that arg structure. So when the program starts, it's here have a pointer, and so the first thing the SPE program does, well, I'm going to take your pointer and get what it points to, because that describes what I'm about to do. From there, this next part synchronizes that, so these fetches are all asynchronous. You issue them, you say, go and get it for me. I'm going to go do something else while I wait. And when you run out of things to do, in this case, well, I can't do anything until I know what I'm supposed to draw, you stop and you say, read, this essentially means wait until all the transfers are finished, and then I'll get on with what I need to do. So then various values are read from the args structure, and our rendering routine is set up, and then we proceed. You notice there's two variables particularly calculated, bytes per row and rows per DMA. So what it does is it says how many rows can I do at once, how many will fit in one 16 kilobyte transfer, and then it goes, and so it loops through going, I'll do that many, and then that many again, and that many again. So it just keeps doing them in less than 16 kilobyte chunks until it's finished. So let's run that one. Oh look, it's still kind of boring, a bit slow. In fact, I'll stop it, I'll run it again and time it. But it will be interesting to see. Is it faster to run it on the SPE with all this overhead of manually copying stuff backwards and forwards? Wouldn't it be just faster to run it on the PPE and let the, just stuff gets written out to memory straight away? I don't have to worry about this extra overhead or all this other nonsense. Is it actually a benefit to put it on the SPE? Or is it going to keep looping and rendering for me? I've set it up in the wrong mode. Suffice to say, it's faster. I don't know if you're able to tell whether it's faster or not. But it is actually faster to run it on the SPE. Now this I think is in and of itself a very interesting result. That the SPE, for a number of different types of program, even without any changes to how the program runs, it's actually the same code that's doing the computation per point. And it's just taken from one place, compiled for the different processors, so there's a different instruction set architecture, there's lots of difference, but you just say GCC, compile me one for this, SPU GCC, compile me one for the SPE. And time for this one, 18 seconds. 18.25 seconds. So we can see there's actually, it's not a small improvement, it's quite a big improvement to go from one to the other. So the next step, actually I'll pause and take a breath. Are there any questions at this point?
It's 3.6 meg.
3.6 meg. Not a question, but thank you. Yes, thank you, 3.6 meg. So, quite clearly, way too much to fit in the local store memory. Any questions? Yeah?
Yeah, so you said there's a second program that compiled the program for the SPE. Is it helpful that you get more a bit less complicated workflow than that. I mean, how is the code that is running the SPA segmented from the code that you write for the PPA in terms of file? Do you refer to a function in another segment, or do you?
Good question. If we have a look in this folder amongst the noise that's in there. You'll see. I can't double click on it because it won't put anything on there. Down the bottom, SPE fractal embed.o. So what happens is the SPE fractal.c source file is compiled into a standalone program. You can actually try running it, it'll just segfault because it doesn't have the argument parameter set properly. But you can actually, and in my research, most of my research is done with standalone programs that do their own thing independently on the SPEs. But in this case, we compile a program that expects certain parameters. What we do then is you take that SPE program and you embed it in an object file for the PPE. So that's the SPE fractal embed.o. That's that embedded SPE program object. And then for the PPE program, you basically tell it, there will be a symbol at link time that has this name. There will be an SPE fractal symbol. So you write it into your, in fractal.c, you'll see.
So half the program is half using machine language and the other half is SPE machine language.
Yeah. So they're separate. So you see here this loading part. This stuff here, the context creates, and particularly the program load, is saying there will be an SPE fractal object of some sort, of the right type in the right place, and then basically the linker and the embedder and the linker do the magic of packing it all up so it all connects together when you compile it as one big program executable. So your SPE program is tucked into the program. It doesn't have to be that way. You can actually have them as separate programs which you load by a slightly different mechanism. But it's nice if you're distributing stuff that's all packed in one blob and you don't have to worry about copying with other files. So, any other questions at this point? Up the back?
I was just wondering why, if you're aware of it, why have they actually stripped down the PPE processor to a point where that it is slower than an older processor when you could go the older processor in case?
Good question. One reason is actually so you can run it at a higher clock speed. A lot of the things that have been left out, instruction reordering functionality and branch prediction functionality, and a few other things that have been reduced or taken out, as I understand it, have been taken out because they were inhibiting the pushing of the processor at a high clock speed. So why would you do that if it's slower overall? One of the things I did say before is that particularly for unoptimized code or badly optimized code, the processor is about that fast. As compilers have got better and as compilers do get better, that will be less the case. You've caught me out on making generalizations and hand waving and not being specific enough. So, any other questions at this point?
So comparing between the SPE and PPE,
Yes?
SPE is better at this
the SPE is very good at single precision floating point in particular. For this exact stuff, I'm not sure if I'm unprepared to make a claim that one is better than the other specifically. But for this program thus far, it is better. And in fact, one of the reasons why is that the overhead of doing the memory transfer is now explicit. Rather than on the PPE, you have writes back up to main memory happening through the automatic memory cache, which is nice and general and designed to handle a wide variety of circumstances. The use of the DMA controller to say, take this block of memory and dump it into RAM for me, is nice and fast by comparison. You don't have to worry about all sorts of side cases, you just go and it's done. So there are advantages to doing it this way. There's reasons why it's faster. Again, I'm hand waving a bit. So. Alright, we'll continue on to the next one. So, alright, if we have a PPE, so this is all on the same processing core. None of this is actually using the graphics hardware of PlayStation 3. Mainly because you don't have access to it at all under Linux. The only thing the graphics hardware does, in fact, is every refresh of the screen, so 60 times a second, it copies from system memory to graphics memory, so it does a blip so that it can actually be displayed. And the way I've been drawing the fractals with the sort of progressive down the screen thing. It's a horrible, nasty way of drawing to the front buffer, and there's no concern for VSync or anything like that. It's quite ugly, but it's beside the point. So the SPE. The SPE is good. In this case, we've got a faster program with not too much work. Can we make it faster again? And yes, we can, because we have more than one SPE. We've got 6 of them we can work with. So presumably, we can take this problem and we can split it into 6, and we can get it done faster. That sounds like a good idea. Let's do that. So we'll run it first, and we specify now. You can't see it on there, but we specify the number of SPEs to use. So we use 6. Look at that. It's all split up. It happens nice and quickly. That's great. Let's do it again, and we'll time it this time. Good. Time it. And 4.138 seconds. 4.138 seconds. 4.14. Now, 4.14 times 6. Anyone? 4 times 6. 4 times 6? 24. Thank you. What's 1/6 of 18? 3. Very good. Good. Basic. So, is there something not adding up here? We've split it into 6. Is it 6 times faster? No. I'll run it one more time. Can you tell me why you think it might be that it's not 6 times faster?
For some reason it's out of sync.
It's out of sync.
Well,
it takes a different amount of time.
They're not
The middle
generating
longer.
they're similar.
Exactly. Very good. They take a different amount of time depending on how it's split up. Now, this comes down to how, this needs to understand something of how this is wrong. The blue bits, in particular, the blue bits are where the point has not escaped. So we have a threshold for the number of iterations we do. It keeps multiplying, and it finally gets to a threshold and says it's not going to escape. I give up. I'm going to colour it blue and be done with it. And so that's where most of the work is. That's where most of the time that this takes is being consumed. So run it again. You'll notice that the one that takes the longest has the most blue to draw. There we go. So one way we can improve this, again, is to split it up. And not, we've split it into 6 parts, but split it into smaller strips. There's other ways you can do this, but in this case we'll split it into smaller strips so that each of the SPEs gets one of the more blue sections to work on, for example. And so that should help further to improve performance. So if we run, now this is, I did forget to mention at the start, very rude of me. This whole demonstration is based on some source code from a guy who works at the IBM Open Source Development Labs in Canberra. Jeremy Kerr has made this stuff available via his blog. I have to provide the URL to that afterwards. It's an interesting blog if you're at all curious about PS3s and Linux and whatnot. But most of this code is based on his work. This is not mine from scratch. Just to make that, my point here is to not say, look what I've done. My point is to say, look at how the PlayStation 3 works. So please don't confuse those points. So now, and then this is one area where I've made a change. If I run this now, this is the more split up version of it. We run that. Well, it renders nice and fast, but I like the whole in separate strips thing. It just sort of ends up being top to bottom because each of the 6 strips, the 6 SPEs do the top bit, 6 SPEs do the next bit, 6 and so it looks like, as it renders, it stays all pretty much in order as it goes from top to bottom. That's not as fun. So I actually did modify it to look more like this, which I thought was like interlaced GIF, looking back to the mid-19th. So there we go. Both of those run at about the same speed, and if we time it, what we'll find is that we're much closer to where we want to be. 3.07, was it? 3.107. There we go. So that's much closer to our 6 times faster goal. So we've gone from 1 SPE 6 SPEs, and it's faster. So, good. What's next? I'll pause again. Are there questions at this point?
Could you get the PPE to do some as well?
You could. You could. As we go on, trying to do that appears to have less and less benefit. The other part of it is the original program that this is based on. The original program that this was based on used the PPE to actually, rather than draw it to the frame buffer, put it on the screen, would generate a PNG file. And so the PPE ended up compressing the image while the SPE is generated. The other thing is that in general that's the wrong way to approach the problem. This architecture, one of the philosophies of this architecture is to take your workload and get it off the PPE. Leave the PPE for doing the boring stuff, the interactive stuff, the things that need quick response. Yes, you could use it to get more performance out of it, but it's generally not of benefit. It's actually nice to have 6 things the same doing the computation, so you only need to optimize your important code once, and then just leaving the PPE for control and management kind of tasks. Yeah?
Was the purpose of increasing the clock speed of the PPE as much as possible to speed up context switching and things like that, because it's designed for those sorts of tasks?
I don't know that it has to do with context switching as such. The design overall, it's not just the PPE that has had stuff you could say left out. The SPEs as well have almost an absence of modern processor features in many ways. They don't have instruction reordering. They don't have any kind of dynamic branch prediction. There's a lot of things that you would assume you would find on a modern processor that are absent from it. They don't have a cache. They have local store memory instead. So there's a lot of decisions that have been made to maximise the frequency they can run at, to minimise the power that the processor consumes, and to actually minimise the memory bus traffic as much as possible. So by letting each SPE manage its own memory, you actually reduce the need for mandatory, say, cache coherence traffic, which on Intel type platforms, when you have multi-core, heavy memory usage stuff, that's where that gets saturated very quickly and performance drops because the memory bus can't keep up. By making them explicitly managed, you make it possible to stop that problem dead. We'll continue. So, oh, sorry, one question? Yeah?
Just a quick query. When you talk about this 256K of memory, is it in fact like a memory chip, or is it actually 256K of registers?
No, it's 256K of locally addressable memory. There are, as well as that, 128 registers. So, by understand, lots of registers, and every register is actually 128 bits. So most instructions act on the register as a vector of data. We'll get onto that a bit further in the next section. In fact, thank you, there's my segue. Next, we'll be looking at the large registers. So the SPEs are, again, targeted computation. They're actually doing really fast. They're designed that they have there's a fusion, so you can do a multiply and an add at the same time as it takes to do a multiply. So you may recall, there's a multiply and an add there. That should be pretty fast, and it is. But the compiler does a decent job of actually mapping what instructions in that case, most of the time. Rather than that, the thing we can take advantage of here is that we do have these wide registers. We do have 128-bit long register, which can hold 4 single precision floating point numbers. So up to now, we've just had our floating point number there, and the rest of it has been sitting there being multiplied but being ignored. It's not doing any work for us. Instead, it'd be much nicer to have 4, and say if we're doing a multiply by another 4 to get a result of another 4. If we can do 4 things at once instead of 1 thing at once, won't that make it 4 times faster? We like to hope so. Let's try it out. So, I'll have a closer look at some of the changes for this one. So, as we go through, colour map is the bit that actually converts the number to a specific colour, but we have this render fractal function. Now, whereas before we had float CR, CI, ZR, ZI. So this is the real and imaginary parts of our equation. We now have a vector flow. So we're going to do 4 pixels at a time. So 4 pixels all beside one another, treat them in one set of operations. And for the most part, that's actually really easy. We just go, well, most of the things we had before as sort of scalar variables on their own, we'll just make them vectors and treat them as 4 at a time. And so we need some of the constants need to be spread out to take up 4 spaces. There's this instruction called SPU splats. It's an SPU intrinsic, which means it maps to a very simple assembly language alternatives. What splats does is takes a scalar number or scalar variable and actually copies it to all 4 or as many as depending on the data type of the slots in a vector. So we splats those numbers out across the 4. And then we come into the loop. There's a bit more splatsing going on. And then when we actually get down to the computation, this is ZR times ZR. That's what it was before. But the compiler does the right thing, and where we say multiply this vector by this vector, we don't need to do anything tricky. It says, okay, that's a vector multiply. You want to do the 4 items times their 4 respective other ones. And so we get this 4 at the same time without having to write extra nasty horrible code. I'm going to pause again. Any questions at this point? 8 minutes? Wow. All right. No time for questions now. We'll have to keep going. Apart from that though, one of the things that does change is how you actually work out if it's passed the threshold. Has the number escaped or has it passed the threshold? And instead of a simple comparison, a greater than, what we have in here is we do need to do a little bit of trickery to do a 4-way comparison. So instead of say the multiply, if we were saying greater than, less than, greater than or equal to some other set of 4 numbers, what we end up with as a result is if this is greater than or equal than this, we get a vector full of 1s. If this is less than that, we get a vector full of a slot, rather, full of 0s. And so we get essentially a mask that we can then feed to this next instruction down here, next intrinsic, called SPU cell select. And so what we do with that, we take these 1s and 0s and say, where the slot contains 1s, or where the bit contains a 1, we pick from one of the vectors. Where the bit contains a 0, we pick from the other vector. So we can actually do combining of the results using this bit mask, using these 1s and 0s. So if it's a 1, pick from the first one. If it's a 0, pick from the second one. And so we can do these 4 multipliers at once, but still pick out just the ones that are interesting and get the right results. So without further ado, we'll try running that. Oops. What is oops? Oops, what is oops? And in fact, if we time that, 0.447. Now, mathematicians. 9 times faster. That's not the 4 times faster we were hoping for. We've got some bonus times here. Where do they come from? One of the difficult things with working with this kind of stuff for the SPEs is that sometimes the compiler gets in your way. Sometimes the compiler surprises you and you get lucky. Doesn't happen very often. I discovered it last night and I was kind of upset because it ruined my nice 4 times faster assertion. So what's happening here is that because in making this vector operations, we've actually simplified it, and the compiler is better able to analyze it. So in the previous case, what it would have to do is to take each individual component out, shuffle it to the preferred slot, process it there, shuffle it back, write it back to memory. In this case, it just goes, I take my natural, I like vectors. I can use them all without doing any shuffling or anything. And so the compiler's able to do better analysis and able to generate better code. This is something you get for free sometimes, but more often than not, when you're writing C and trying to compile it for the SPEs, you just run into brain-dead compilers that don't want to help you. Lots of work is being done on that, but it takes a long time to get complex code turning into efficient code. If you want really fast code on the SPE, you write it in assembly. and you time your pipelines and all the rest by hand. But in this case, this is what we have. It's much easier to understand this way. So, the next step. Is there a next step? Well, there is actually a next step. What can we do next? One of the other things is not only are the vectors, the register is very long, able to hold 4 elements, there's lots of them. And if we look in the inner loop of that previous implementation, the inner loop actually isn't very long. There's not a lot of stuff between here and here, although this is the loop where most of the work is done. So one of the techniques we can use here is one called unrolling. So rather than doing what's in the loop once, what we can do is actually do that body bit multiple times and then decrease the loop, well, increase the loop counter. So rather than increasing it by 1, which is what that I++ is doing, we increment it by 2. And so we step through quicker, but do twice as much work in the inside. And so if we have a look at this one instead, you'll see that what I've done is essentially just copied and pasted the inner guts of that loop and then stuck in a I+ equals 2 on the end. Now, we run that, and that's stop. No, it's not. There we go. One of the other things, this is, I'm not really trying to hide anything here. One of the other things that happens is the first time you run an SPE program, the overhead is higher if the actual program's not cached in memory. And that turns out, in terms of the actual load time of a naive time testing thing like the Shell's time program, you've got to run it a couple of times and then it tends to stabilise on a meaningful number. So, we're down to 0.340 by just copying and pasting a bit. And in fact, if we go to the next generation and run it again, oh, there we go. This is my looping one. We're now just running over and over again, looping through, and you can see it's almost fast enough. It's a bit speary as it runs. But this is with, from memory, 16 iterations of that inner loop. So rather than just doing it 2 at a time, it's doing 16. The reason why that's faster, the reason why that goes faster with the, is because it actually gives the compiler more instructions to work with as it schedules what it's got to do. And you can see it just keeps panning across the fractal space. Isn't that pretty? And I killed it. But, well, basically I'm done. I'm out of time. You need to leave. So as we finish, I'll leave you with a Zoom. And are there any further questions as that reaches the limits of single precision floating point-based representation? Any questions?
Are you using research for optimization or?
Not as such. This has almost nothing to do with my research. I didn't talk about it yesterday as in a research seminar, but my research is on actually, for these SPEs which don't have a software cache, don't have a memory cache, trying to implement a software cache for them. So when you're trying to port a program to the SPE, to minimise that need to go from, here I've got this nice working program with complex memory access patterns, and now I need to write myself a memory manager. Basically, here's one that was prepared earlier and is pretty good, so that's what I've been working on, and it simplifies that process of getting the program running on the SPE, and then you can optimise it and improve it from there. So that's been my research. Yeah, cool. Yeah?
Can you give a summary of what other hardware is in the box as well?
What other hardware is in the box? So the processor, there's the RSX reality synthesizer, there's the graphics chipset, which is an NVIDIA 7000 something series chip, which is okay. Most of your run is in the SPE, particularly for game stuff. Yeah, it goes, it resolves to some sort of 8-bit awesomeness. I love it. Anyway. And other than that, there's a Blu-ray player. There's it's one of the original ones, so it's got backwards compatibility to PlayStation 2. It's good for games. It's also okay for research.
Have you tried using perhaps a development kit to analyse the sort of thing on their GPU?
Development kits are somewhere around 10 grand, or I haven't. No, I had to buy my own PlayStation for my research. So yeah, it was a tragedy, and that's why I've only ever used it for research. Yeah, so no, I don't have access to a dev kit. There are a lot of tools from IBM that make you can do it. Let's run it again. There's a lot of tools from IBM that have a software development kit. You can install Linux easily on a PlayStation 3. It's pulled it out of the box. So you basically pull it out, download a bootloader and an install CD, and you can just partition your hard disk and all that sort of stuff. Minimum fuss. Yeah.
You said that Martin is a very specific. Is that market decision or?
That's a decision from within Sony, and I don't know any more about why that is.
Homebrew, essentially.
Yeah, homebrew is, look, it's made it possible for me to do the research I've done, which is of some value to the Cell development. Some value. But, yeah, for whatever reasons, apparently I've heard suggestions that it was intended that there would be more access or different access or better support for that on PS3, and that various reasons had to be.
There's no access to what?
There's the open source Mesa, which is available software. There's been an effort to port that to use the SPDs, but OpenGL doesn't map especially well to them. OpenGL ES, for example, is better, but there's a lot that's working on that.
In your talk yesterday, you said that normally a software system has 8 SPDs. Is that right?
There are, a full Cell processor has 8 SPDs. In the PlayStation 3, there's 7. And one of those, 7 for manufacturing yield purposes. So basically, it's taking the ones that didn't work good enough to sell them in the expensive servers and sticking them in PS3. And then one of those isn't available because it actually controls the hypervisor, which is the bit that keeps you from accessing, to some extent, the graphics hardware, or at least mediates access to the hardware.